I have to press share screen. Share screen. Okay, and here we go. Okay. All right. Okay. Thanks, Zishan, for the introduction. Be nice to Zishan. He has a lot of work preparing that course. He gets a lot of questions. It's not so easy to handle all of that. So thanks, Zishan, again for your hard work on that. Okay, so as you also just said, a very important part of this course is the opportunity that you have that you ask questions, and I'm very happy that many of you do that. And yes, if you have questions, we suggest now to write them in the chat, and then I will try to answer them at the end of the course or latest beginning of next course, as we are doing it now with the questions from last time. Okay, questions, right? So, okay, questions that came up were, why is SAR side looking and not nadir looking? Same question, what happened if the incidence angle is 0, nadir looking in SAR? So let's look at that. And that picture is a bit blurry. Do not worry about it. Okay. Anyway, so right. What you have to understand is that the SAR system works a little bit differently from laser or optical, obviously. Okay. And so what is different is that you have a rather large radar lobe. So if you look here, you have the transmitting antenna, and it's not like a very ugly drawing. It's not like a single beam going out, okay, like that. But you have instead such a rather huge radar lobe. Okay, so that is very, very wide. So if we transmit one signal with the radar, one pulse, right, it's not going to be a very small beam. It's going to be like, or not like a very small ray or something of light. It's going to be a very huge, wide radar lobe that's going to cover a huge area. Okay, so this is the main point that you need to understand. Okay. Now what happens? Now what happens if we turn that one around? Right. If you're now looking downward. Okay. So now we would put that radar beam in nadir direction. Right. Yeah, let's assume that that black line is the ground. Okay. And what now happens is that at these 2 points, right, they have the same distance to the sensor. Okay, so the signal reflected from these 2 points will come back. The reflection will come back to the sensor at the same time. That's to say, we cannot separate now the left side from the right side of the radar. Right, these would come back at the same time. It's ambiguous. I get a signal, but I don't know if it's on the left side or it's on the right side. So my image would be here divided somewhere in the middle, and I don't know what's left or right. Okay, because that's ambiguous then, because the signals come back. So I can't really do that, right? So, but if we are looking toward the side, right, then I can separate the signals by their running time. Right? I can separate beginning from the image towards the end of the image just by looking at the time when I received that signal. So we can't look nadir because we cannot then separate the signals correctly. Okay. Anyway, come back to that a second. The key point is also on how synthetic aperture radar works and why we even need a synthetic antenna, is that the radar lobe that we send out is very wide. So we get, if you want, we get a very bad resolution. And if we're looking downward, we cannot separate left from right side. If we do not care so much about that, right? For example, in radar altimetry, we do not really care about that. We can do that and live with the very bad resolution that we would then have in terms of that. Okay. Is it possible using SAR to detect long sunken channels like the branches of ancient rivers? And I did like that question because actually there is some work some colleagues and friends of mine did on this. This is here. I forgot the name. It's some site, I think in Turkey. It's some site in Turkey where they actually worked on that topic, and then follow here that path of the ancient river here that actually changed. That river changed the course, the flow direction then in historical times. So the idea of that is, the question behind it was an archaeological question. It's like, why were some settlements that have been found, why have there been at that position? If you normally set up a settlement, you build it next to a river, okay? So, but that was not the case here. So the question was why, and so they were looking for ancient rivers, and then they found that actually some of that settlements and stuff they found were actually close to an ancient arm of that river. So that made much more sense. And the way they did that here, to look for sunken channels, they used two parts of radar. Here, one was they created a very high resolution DEM then from the Tandem mission. They used that, and then they also looked at the so-called coherence of the data today to see changes in the coherence. But already what you see on the right side is just the DEM, where you already can follow that quite well, actually, that old river. So the answer is very clearly yes, you can do that, and it's actually already practically done. There are many ways to do that. You know, the DEM, soil moisture differences, because normally your ancient river arm still has different higher moisture typically than the surrounding. So yes, actually SAR is very capable of doing that. Okay, now another one question that is very great for me to answer. That is the speed of moving object. Can the speed of moving objects be identified using the effect? And how to differentiate horizontal vertical motion? Now I have to say, the second question on the horizontal and vertical motion, that question may be more related to INSAR and the motion of surface motion. And in that case, to the questioner, to the person who asked that question, we will come to that in much more detail during the course, okay? And if then you're still not satisfied, you can answer that question then again, okay? So I wasn't sure if you are relating to also to the motion here, the motion of fast objects, or more the surface motion that we discuss with interferometry, probably next time, starting next time. All right, so let's come back to that question of the car. So first of all, when we have a car moving here toward the sensor, right, that car is displaced, right? It is not mapped in the SAR image, not positioned in the SAR image at the correct position on the road, but it will be placed somewhere beside the road. That's also not only true for cars, that's basically for every moving object. So there's also many SAR images where you can see then moving ships through a river, who are actually where you can see the ships appear on land, or some effects like that. So moving objects will be displaced if they move toward the sensor. There will be mapped at the wrong position, and if they move in the direction with the sensor, okay, along track with the sensor, what's happened is then that they will be smeared. They will be, well, getting blurred, if you want. Okay, so they're getting, basically that's similar to optical effect, and that they get blurred from the motion. It's a motion blurring with the object. Okay, but can we get the speed of them? That was the question. Also here the answer is yes. I'm happy you asked the question, so I can show the work of my student here, who was working on exactly that topic. We had here, we were looking, that's one bridge in Wuhan. So we were looking at cars moving over the bridge. So you try to identify these points next to the bridge, separate them from what's probably a ship, right? And then by measuring the distance toward the bridge, right, we can then estimate the speed of them, because the faster they are, the more they will be displaced. And here on that side, here we estimated the speed of these different targets. Oops. So you see we had then, well, the right side, there's one line missing. Anyway, the right side of the table, the right column, that's then the overall speed. The left side is the speed in the direction toward the sensor. So that's just a part of the overall speed. And you see we estimate them with around 60 or less than 60 kilometers per hour, which indicates also what in this case that we are assuming, what we assume in that case is that we are not really seeing all cars, but mostly the larger one, the trucks and buses, because their backscatter is higher, and some smaller cars we maybe misinterpret them as noise or something, right? Actually, the student then used that work toward counting the overall traffic over all bridges in Wuhan. At that case, over time we can see a certain increase in traffic, and then we use that and also compare to traffic parameters during the military games and the COVID-19 lockdown in Wuhan, where we can clearly see these events with much less traffic. So the answer is yes, you can also measure the speed if you're able to clearly identify the targets. There is also another way to do that. I didn't really explain that. I think we have a slide on that. Probably next time or next time we talk more on that. Where you can get the speed much better by using interferometry and antennas in another direction. Then we can measure also speed with more precision, right? Instead of just like measuring that the shift in azimuth direction from the motion of the car, right? So yes, it's possible. There are also different ways of doing that. And let's not forget, radar in itself is a good speed measuring tool. It is used to measure, traffic violations and speeding. So it certainly can measure range. It's very good at measuring differences in range, and at the end, a speed measurement is a difference in range measurement. All right, okay, so then we had a couple of questions toward the stereo radargrammetry on the opposite configuration. Why is it more accurate? Right. I come to that. How to differentiate ascending descending for structural geology? I don't know how to answer that, actually. I don't know what we should differentiate there. And what is the importance of incidence angle in these images? Now, I'm not exactly sure where that question goes, but let's take a look at the stereo radargrammetry. So in stereo radargrammetry, in the same side configuration, okay, we're looking from the same side with a certain difference in the incidence angle. Okay, and we get a better geometry. That means a better, at the end, a better solution of our DM calculation if our incidence angle difference is rather large. Okay, so let's just say if it's pretty much similar to optical in that sense, right? If you have two cameras or your two eyes are very close together, you get less of a 3D view than if your cameras are very far apart from each other, right? You get a better 3D solution when your baseline between your two cameras is more large. And that's the same case in stereo radargrammetry. So if these two images that are very, if our second image would be here, with a very small difference between these two angles, they're almost looking the side. There's not going to be a lot of difference in the looking angle. There's then also not going to be a lot of difference in the shift, in the range shift of this pixel. There's not a lot of difference in the geometry of the final image. So you're not going to get then a good DM out of it because you're looking at the difference between the two images, right, between the range shift. And that difference is larger if we have a large incidence angle difference. So the angle difference should be rather large to get a good configuration. Now, if we have opposite side configuration, our angle difference is even larger. Okay, so we get even a larger difference between these two images, right? How to say? Okay, so if you have a very high point, like here, this mountain that I mark here, right? What is happening with foreshortening and layover is that this mountain will be moved toward this direction, right? It will be displaced toward the sensor. And in the opposite side configuration, this from this image, the mountaintop is displaced more close to the sensor in this direction, and it is more displaced in this direction toward this one. So the difference between these two images is much larger. Okay, we have a much larger difference of the geometry from the opposite side configuration. If you have a larger difference, it's much easier to find even small height changes, because even a small height difference these points will move opposite. So easy to find if you were able to clearly identify here the mountaintop, for example. So you get a much better solution and you get a better DEM at the end. The problem is, though, the larger your angle difference on the same side configuration, or also on opposite side configuration, where we have a very large difference, right? The more difficult it is to find the same point in both images. Okay, it's going to be much more difficult to identify. Well, this is the same road, for example, in both images. This is the same pixel. This is the same building in both images. So it's going to be much more difficult to identify that, and therefore you have more problems finding these homologous points and then creating then the DSM out of them. So the opposite side configuration in theory gives you the better results, the better solution. But in practice, it's much more difficult to find the same point in both images. And especially in mountainous areas, right, where we have then layover and shadow. You see lots of this mountainside you will not see from the sensor, for example, at all. So there are many points that you only can see from one direction. So it's not, for many pixels, it won't work at all because you need to see both. You need to see the same pixel in both images. So in practice, the opposite side configuration can mostly not be used, especially in mountainous areas, which is, mostly the areas where we're most interested in creating a good DEM. So therefore, although it's giving us a better solution, a better configuration in practice, we seldom use that because we cannot find enough similar points then. I hope that made a bit more sense now. Okay. Now, what is the accuracy of DEM by radargrammetry? There is not an easy answer for that. Okay, but if you use radargrammetry, okay, the accuracy that you can achieve depends on the spatial resolution of your system. So let's say you can identify the same pixel in both points, maybe on a pixel level, maybe in subpixel precision, right? Maybe half of a pixel, right? Something like that. But because it's on the pixel, it depends on the pixel size. So at the end, your accuracy also relates to the pixel size, to the resolution of the system you're using, right? So that's to say, if you have meter resolution, high resolution data with meter resolution data, you will get something in the, a bit less than meter, right? But something in the range of a couple of meters, depending on how good you can identify the homologous points. Now, if you have 10 meter pixel size, then you will be like,
Recording stopped.
More on a round of a couple of tens of meters.
Recording in progress.
Of it. So it depends on the pixel size and then how fine you can identify them, the homologous points. That depends a bit on the underground. Okay, so what does that mean? If you have lots of structure, lots of edges where you can really identify these points, probably even in subpixel accuracy, you get subpixel accuracy. If you have a very homogeneous surface, right, where every pixel more or less looks the same, you're going to have problems identifying them, and then you probably have to multi-look and reduce the resolution to get to somewhere, reducing the accuracy of your DEM even more. The key message is, with radargrammetry, your accuracy depends on the pixel size. Well, this is not true for the interferometry that we talk about. There, in interferometry, at least in theory, theoretically speaking, the accuracy only depends on the wavelengths of the system. So, and it's normally a higher accuracy than with radargrammetry. But I cannot really give you one number. Just keep in mind, for radargrammetry, you talk, in the ballpark around what you have in resolution, in spatial resolution. Typically for radargrammetry, we multi-look, we downsample it a bit. So, you get typically a little bit less than that. Now, what will the accuracy difference between C and L band data for DEM generation? Now, which way of DEM generation would be the question, right? In radargrammetry, it would depend not on the wavelengths, but rather on the pixel size of it. Okay. However, in interferometry, in theory, C-band will give you higher accuracy than L-band because it's a shorter wavelength. However, in practice, that may not always be true, right? Because L-band is less affected by noise, and depending on the overall situation, may work better and give you at the end even a better accuracy. However, like just theoretically speaking, by the book, C-band will give you higher accuracy than L-band. In SAR and for radargrammetry, it depends on the pixel size. All right, that's the next question is a very good one. Although we didn't really go there yet with coherence, but doesn't matter. Is correlation related to coherence? And the answer is yes. Okay, it is. I put you here the two equations here a little bit unsorted. I just copied them in. So that down here would be the correlation, the way we calculate the correlation, and that here is the coherence. The main difference between the two is that for the coherence, we use the complex data that's including the phase. And so we use the complex conjugate multiplicator to do that, which is at the end a subtraction of the phase. So we are still at the end, it's very similar to here. We're subtracting one phase from another. So both of them are rather similar. You can understand the coherence as basically as a correlation, including the phase. That's a little bit simplified, but still good enough. So they are very much related. They're very much related. They're not identical, but they are related. All right. Okay, that has been the questions from last time. Keep on asking. Okay. That also helps me to understand what did I maybe not explain enough. Okay, that's also important. All right. And today we start with the rather huge topic now. The main topic of that lecture is on the SAR interferometry, where we look at phase differences. So SAR interferometry is, well, as old as I am, right? So rather old in that sense. The very first one is from radar for topographic mapping from Graham. 1974 is the first mention of it. Basically, looking here at these, on the left side is the radar image, looking here at these fringes. These are these fringes we call these lines that you also see here. We come to that a lot. These phase difference lines, if you want, called fringes. And I think they basically saw that on the radar image that looks very similar to a topographic map. So there was the first way of thinking about, well, that we could maybe use that to create DEMs. And this comparison with these fringes with DEM I will also use to explain some of these phenomena. Then the start of it, more or less, then is more practically is around the beginning of the 90s, end of the 80s, with Goldstein's paper on phase unwrapping, which is a very essential step to come from these lines, from these fringes toward actually a DEM. And then a famous paper from Massonet et al. In 93, looking at how the Landers earthquake look in radar interferometry. So then the first clear proof of motion detection with radar interferometry, because what we here see is the motion from an earthquake. Right. So these are the, we can say, the milestone papers that showed the possibility of using SAR for DEM generation and then for motion. Now, in our course here, we are focusing on the motion part, but as the methods are developed also for DEM, we're gonna start with explaining how we create a DEM. So, because that includes all the different, it's two reasons why I start with that. One is it includes all the problems that we later face again, and gives a good introduction into the interferometry, and it's also more or less how the discipline developed from DEM, moving more towards motion detection. Right. Okay, that's an important slide because it includes many important terms that we always gonna use. Okay, so again, we need for interferometry, we need two antenna, two images from a slightly different position. You can achieve that by having two antennas on one satellite, on one airplane, okay, or you have, as is shown here, a satellite coming in one orbit and then having the satellite coming back, after he go around the Earth and the Earth turn around him to come back at the same position in the second orbit. And from these two images, you can then form these interferograms, these fringes. Right? So we're having, we're looking in azimuth direction. That is here, azimuth. So we're looking here along here in this direction. That's the flying direction of our sensors, and the measurement is in this direction, the looking direction of the sensor in the so-called slant range. That's also the direction in which we measure everything. So the DEM, or the motion we measure, is measured in this slant range direction. Sorry, a bit, not so straight line. That is the measurement direction that we are having. And then important word is the baseline, right? So we have the interferometer baseline, that's the distance between the two. But normally we're not using that distance, we are using that perpendicular baseline. That is the perpendicular distance, you see, from this one to the slant range. So this green line, that's the perpendicular baseline. Why are we using that one? Well, if you look at it, if we do that, we can form from here, that's a perpendicular triangle, right? We're looking at the perpendicular baseline because that's a perpendicular triangle. And then we can do trigonometry, right? If we have a perpendicular triangle, we can do trigonometry. And that's basically what we do. At the end, we're using trigonometry, looking at then differences in the distance between these two, and form here like can then form a perpendicular triangle between them. So that's why we typically look at the perpendicular baseline. That is the distance between these two images in space, right? The original distance between the two would be the interferometer baseline, but the value we need for calculations is the perpendicular baseline. That's very important for you. And then we, in interferometry, we very often talk about baselines. So we have the perpendicular baseline, that is the spatial distance between the two. And then we often also call the temporal baseline, which is then the time difference between these two images. We call that the temporal baseline. So we talk about a spatial baseline, temporal baseline, perpendicular baseline, or temporal baseline. These are the terms that we are using, and that's a term that you need to know here from that slide. All right, so we call that a cross-track interferometry. That's a bit also another term that is, yeah, well, important. Yeah, it's also important. At least you should know it, right? A Crosstrack, because if we look at this image, we're looking. So if our satellite flies, the track would be the azimuth direction, the direction the satellite flies. So inside the camera from my position, okay? And we are looking at the side, right? A cross track. That's the looking direction of our sensor, okay? That's what we measure normally, and that's called the Crosstrack Interferometry. Right? We can also measure, we can also position our antenna in this direction, and it's a long track interferometry. We can use that to measure these fast motions from cars, for example. But that's not our main topic. Our main topic is the so-called Crosstrack interferometry. Okay, now this is the important equation that comes back all the time. So let's take a look at that. So the phase of a pixel, right? This is the phase of a pixel. We can calculate that, and that depends on the range R, right? The range between our satellite and our object, right? Now, in that range, okay, our wavelength travels along that range, okay? And the phase is the fraction of the wavelength, okay? So one wavelength is from here to here, and the phase is the fraction of that wavelength, where I'm on that fraction. And so it is then calculated by 4 pi divided the wavelengths. We have 4 pi instead of 2 pi because we go there and back. Right? Typically it would be 2 pi. If it's one way, it's 2 pi, because the phase, we give the phase, we give it in radians, in degrees. Okay, so it's because it is like it's this sinusoidal function that is across 2 pi from here to here. Okay, so it would be 2 pi divided by the wavelengths times the range to get to that phase value. It is 4 pi here because it's not range, right? It's not one range, it's actually two range, 2R. It goes there, the signal goes there, and then goes back. So it's actually 2 times R. Okay, so we are landing at 4 pi divided by the wavelengths times R. That's the phase of our pixel. Plus this one, this is the influence on the phase from the scattering of the object. So we hit our object, you know, that can, maybe there is some volume scattering or some edge scattering, or the object is a bit tilted. There might be reasons why the scattering also changes the phase a bit. Okay, so we have also a component of phase change from the scattering. And similar at SAR image 2, right? That's the same, but we can, instead of making here R slash, we can separate that in R plus delta R, where delta R is the difference, right, between these two ranges. Okay, it's just to make the next equation mathematically more beautiful, right? And what we do in the interferogram is, well, we subtract phase 1 from phase 2. That's what we do. And if we do that, we achieve the 4 pi divided by wavelengths times delta R, gives you the phase, under the assumption that the scatterer 1 is the same as scatterer 2. Right? If these are identical, if you match the images correctly, you're looking at the same object, you're looking at the same scatterer, that will be the case. And under these circumstances, then your phase that you get here can be calculated from the range, or from the difference in range between these two images. Now, there's one problem in that slide. That slide is very much correct. Okay. However, we do not measure this phase value here in the SAR image. Because from that equation here, this phase value here, that is what we call the unwrapped phase. That is the absolute phase. That includes the absolute number of all the phase cycles that went through. However, what we at the end measure in the SAR image 1 and SAR image 2 is the wrapped phase. So that's the phase that is the part of the phase that is between minus pi and pi, right? The 2 pi, the fraction in between these 2 pi that we have. That's what we actually measure. So our overall problem is a little bit more complicated than that, because if that would be the unwrapped phase, the overall phase here, we could directly calculate delta R and everything would be much easier. Okay, but we only have the wrapped phase in it. So we only have the fraction of that phase that's between minus pi and pi, because that's only what we can measure, and that's making things a bit more complicated. So this equation here, although true, right? Although true, in terms of what we can measure, is only true if the phase difference between these two is less than 2 pi. If the phase difference between these two is less than 2 pi, then you directly have your delta R. If the phase difference between these two is more than 2 pi, then you are ambiguous and we have to do phase unwrapping. Right. So this is the key problem at the end, right? That what we measure is actually not that here, that unwrapped phase, but actually we only have a wrapped version of that. We'll come back to that, no worries, many times. All right, so let's look at that. So that's a complex SAR image. The left side is the amplitude image. That's what you normally look at. And the right side is the phase image, which looks rather noisy, right? It looks rather noisy. It is at itself basically just noise, right? So again, why we look at SAR, that would be SAR image 1. That would be the wrapped phase of SAR image 1, right? So why is that so noisy? Okay, because it would not be so noisy if all your pixels would be exactly, right? All your backscattering objects would be exactly at the center of each pixel. But that's clearly not the case, okay? So if they're not exactly at the center, then there is the R here, right? If, let's say like that, if at each pixel, they're not exactly at the same position within the pixel, right? If one is at the center and one is a little bit to the left of the center or a bit north to the center, you know, none of them are exactly centered, okay, and always at the same position within each pixel. In that case, the small range differences within a pixel are already so large that they are far above the wavelengths of, or half of the wavelengths of a system. So if you think about an X-band system, right, with 3 centimeter wavelengths, if they are 1.5 centimeter away from the center or from the center with respect to each other pixel, you basically up into noise already. So if you only look at the phase of one image, there is not much useful information into that. So we're not doing that. We're not looking at the right side here at just one phase image, because there's not much to do with that. Okay. Right, that's basically the same. Let me first show that one. So what we are doing is we are overlapping two images and then subtracting the phases. And if we do that, there is still noise until we really overlap them directly very well. Then you get useful information out of that. So the phase in one SAR image, it looks basically random. It's a speckle effect. It's that they're not really positioned always similar with respect to the center. So it's basically noise, right? Or like he formulated here more scientifically, looks random. No. Okay. But if we co-register them and subtract one phase from another, we get this interferogram that you here always see for a short second, which is more similar to a topographic map, and we can do something with that. So the interferogram is formed by complex SAR image 1, complex SAR image 2, and we form the interferogram here by doing this complex conjugate multiplication, which is this operation here, right? Which is at the end, if you look at the phase, nothing else than phase 1 minus phase 2. Okay, so we subtract the phase 1 minus the second phase. And then we're looking at the phase difference between them, and then we come to such an interferogram like here. So I also like that slide. I always laugh when I see that slide, right? So the SAR interferogram formation, we cross multiplying each pixel of the first SAR image with the second one complex conjugated. And I love it because it is so unnecessarily complicated, okay? Because cross multiplying with complex conjugated, that's just a term from the, here, the complex conjugated. It's just a term from complex numbers. At the end, it means we multiply the amplitude of the first image times the second image, which we at the end never really use anymore. But we are using the phase difference between the two images. So instead of cross multiplying complex conjugated, right, we could also say very simple phase 1 minus phase 2. Okay, that's all we do. Okay, so sometimes we make the slides look very complicated to say very easy things. Phase 1 minus phase 2, rather simple. Okay, after you overlay these two images, and then we get something like this. So on the left side, this is the SAR image, the amplitude image, right? In the middle is the interferogram, and we move toward, on the right side, the DEM. And now I use that example often here to explain. Now, if you look at the interferogram, okay, we can understand this interferogram as if it would be a topographic map. Okay, if you imagine these color lines, these color lines would be the ISO lines, the height lines of a map. Okay, so these are the different height lines with each color, and actually we know from one height line to another, we know the height difference. Okay, we know from red to red, that's one phase cycle. Okay, all right, let's say, just for example, red would be pi, then somewhere here would be minus pi, and here we would be back at pi, right? Something like that. So that would be one phase cycle from one color to the same color. And we know how large is the height difference between these two. I will show you in a couple of slides how we know that. We can calculate that. That's not a problem. So it is like a topographical map, and these colors are the ISO lines. But these are ISO lines without number. We know the distance between the lines, but the numbers are missing. Okay, so it would be like a topographic map without numbers. Okay, that's the main problem. So, you see, if you know maps and you worked with maps, okay, then you would know, well, here there are not so many lines on this side here, right? There are not so many lines. That's to say that's a rather flat area. There are not many ISO lines. And then when these lines get very dense, like here, there's some steep mountainside, right? So when the lines get dense, you know, it goes up or it goes down, right? Here the same, right? It's very dense, so it's more mountainous, it's going up or going down somewhere. And in that point, when I say going up or going down, you already get there. Well, it is ambiguous, right? So I know these are the topographic lines that I have, but and I know the distance from one line to the other is how many meters other than height, but I do not know, is it going positive or negative in this direction? Is it going up in this direction or is it going up in this direction? I don't really know, okay? So the main difficulty of the interferometry to come from these fringes, from this interferogram to the DM on the right side, is to fill out these numbers, okay? To put numbers on these lines and do that, and to get to a DM or DSM, right? If you correctly. So that's the main problem. Okay, so to get to that part, to get to the interferogram that you see in the middle, that's the easy part. Okay, the difficult part is then to make sense out of these lines and to get to the DM, because these lines are very much ambiguous. Now, the main problem you can understand is if you would have a topographical map, with all these ISO lines, but no numbers. So you have to figure out the numbers. And if you have a point to start, okay, if you start, let's say here, you know the height here, then you can start to fill out these numbers. Now you must make an assumption in which direction it goes up and which direction it goes down. But beside that, right, you can start counting, right? And then, okay, from here to here, now I'm going up, I have so many meters, and then you can count all these lines here along the mountain. You could get to a height for each point. But, right, it's not easy, especially this is in the middle, is a very beautiful interferogram, almost without noise. You can be assured not every interferogram is so nice and noise-free. All right, okay. So how the fringes look like, the density of these fringes also depends on the wavelengths, right? So we can see that in our main equation here. Here's the wavelengths. Okay, so it clearly plays a role in the phase. And if you have a very short wavelength like X band with 3 centimeter, our fringes, these ISO lines, whatever you think of them, they are very dense, they're very close together. And in L band here, they would be more far away from each other. Okay, so again, we had that question on which one gives us more accuracy. Well, here the ISO lines are very dense together, so we can more accurately get the height of a certain pixel if we can like put a number on all of these lines. Okay, if we succeed in that, it would be easier, it would be more precise to get the height in this X band data here somewhere. However, in the L band data, right, it's clearly easier. We have less lines to worry about, right? We need to count less steps up and down. We would get to some height easier, but that height would probably be less precise, right? And but if we, what I want to say, if we imagine more noise on the data, it's also clear that here it would be much more difficult than if we add more noise here to separate these lines. While here, if we add some noise on the L band data, we could still clearly separate these lines from each other. So under very good circumstances, if we get a very good and noise-free picture, we get better, more precise results from X-band. But L-band can give us also more stability then. And it's also logical and not, they're not mutually exclusive, right? You could combine these two to get something best of both worlds. However, they're also looking at different heights at the end. Anyway, right, the fringes and the density of the fringes, they clearly depend on the wavelengths. All right, so if we look at the interferogram, it's a color map of the distance changes. Okay, so if we assume here, if we assume a wavelength of C-band of 5 point some centimeter, 5.1, something like that centimeter, 5.6 actually centimeter here, then the same color would, from red to red, it would come to a distance change of 2.8 centimeter. Now, if we think about the distance change between image 1 to image 2, right, that can be because of motion, right? And we will come to that, right? Distance can change between two images because something was moving between these two images. But distance change can also be caused by the topography of it. Okay, so because we're looking from different angles, the distance changes are also caused by topographical differences and can be used to create a DEM. Right, and we see that here in the baseline. So we have the baseline between the two. And basically, we are forming such a triangles here to come from baseline, and the range differences then to height to phase differences. You see delta in phase. So there is we can form here a direct relation between the phase differences and at the end the height differences between these. So at the end, let me move that one away. So if we look at the relative interferochromic phase, so that is proportional to the orthogonal projections onto the line of sight of the baseline, the distance between reference point and point B. So what we are looking at with interferometry is always range differences. Right? Range differences, well, it's clear if we look at motion, we are looking at range differences, but range difference are also caused from topography then. All right, okay, let's take a look at how we are doing it. Okay, how are we doing that? How are we processing that? A bit step by step on the steps that you will go through in whatever software you will use to do that. So very clearly, very first one, very simply, is the data import. You start with importing the data, maybe some pre-processing. And then an important second step is the image registration. We need to register the images together so that one image lays on top of the other image. And then we calculate the interferogram. That's rather the easy part. It's just image 1 minus image 2. Phase from image 1, sorry, minus phase from image 2. Then we need to remove the component of the flat Earth. I will explain what that means. Okay. Then we can do some filtering. And then comes the part of phase unwrapping. That's where we start to put the wrapped phases that we have toward unwrapped phase. That's the part, basically, if you want, where we start to fill out all these numbers on these height lines, on these ISO lines. Okay, that's the phase unwrapping part. Then we can start to better estimate the baseline. That is nowadays with modern sensors, this part is nowadays typically not necessary anymore because we get very good orbit data and baseline data nowadays. And then we can start to compute the heights, and we get them in the SAR geometry, and then so we have to transform them into map coordinates to get a DM that we can use. Okay, and the complicated parts here are the parts that, let's say, can go wrong. Okay, that's the image registration, right? Mapping these images together. That is comparably easy in SAR compared to optical data, where you have much more disturbances, but still that's something that can go wrong. And it's also clearly the phase unwrapping. That's a part of the processing that is unfortunately ambiguous and can go wrong, and quite often also will go wrong. So these are the two parts where I would say where you from processing, but if you actually do it, may run into trouble. Now, data import, that's pretty clear. So normally you're going to have to read the data, maybe copy to a new format that's understood by your software. If you get the raw data of the sensor, then you first need to focus, right? What we use for INSA is the SLC data, the single look complex data. If you get whatever ground range data or geometrically corrected data without the phase information, you will not be able to use that for INSA. And then the next step is reading the metadata. It seems simple, but it also includes the orbit, the orbit data. I wanted to highlight that one. So the orbit data, okay, here it is, the orbit data. Now the orbit data, there is, normally we have like a rapid orbit data and a more precise orbit data. Depending on which data you get from where and which sensor and who's providing the data, that precise orbit data may be already in the metadata. But quite commonly it is that you have to download that separately, that you maybe get some more less precise data, maybe it's already in the metadata. But the more precise orbit data is available for download later. And the reason for that, it takes some time. So directly when acquiring the image, the orbit is estimated. Okay. Now, when the satellite goes around, its orbits and its position is continuously measured and is corrected. And the orbit data is later also corrected based on the measurements at the time, right? But that takes a bit of time. You first have to measure it. So that may take a couple of days, okay, between the images acquired and when you can get the very precise orbit data. And that's the reason why quite often you're going to have to download that extra, right? And that's important when we use interferometry. We do want to use the most precise orbit data we can get, right? Then you may need to calibrate the data. Maybe you're just selecting a subset of the data. Sometimes we also produce interferograms on oversampled data. Again, I think nowadays this is less common because we now have, well, our data is, the resolution is already quite enough. I don't think we do that so much anymore, but it's still, you can also process it on oversampled data. Okay, that would be the data import. Then we need to register the images. So we need to define the master image or the primary image and the slave image, also the secondary image, whatever you'd like to call it, right? We make sure that this second image is overlaid to the master so that both the pixel coordinates are identical. So if you look at one pixel, it's the same in both images after resampling. Because after we have done that correctly, then we can just subtract the one pixel, the face from one pixel from the other pixel. But we need to make sure that we subtract the same object on the ground, the same scatterers. And we need to do that very well. We need to do that with an accuracy that is better than a tenth of a pixel, right? That seems to be quite high, is, however, not very difficult to achieve in SAR remote sensing. Right? We can achieve accuracy of better than 0.1 pixel with standard processing, basically. However, for this TOPS interferometry, when we use TOPS images, we need a much higher accuracy. I hope you remember TOPS. TOPS was the mode where we started looking backwards, switched to moving forward, and a little bit complicated mode. It is important now that because that's the mode Sentinel data is acquired, and we often use Sentinel data now, well, because they offer global coverage and are provided for free. So we do like free data. So we have to deal with TOPS, right? And if we use TOPS data, so if you use Sentinel data, you need a much higher accuracy than 0.1 pixel in registration. So you need a different method. There are different methods available. Typically, we base it on the amplitude. We find, by looking at correlation, we find similar looking pixels, and then we match them. We can also do it with complex data, not looking at the matching in the amplitude, but at a maximum of coherence instead of a maximum of correlation. You see, it's very similar things, okay, because we had that question. Here we would look at a maximum correlation, but we can also look at the maximal coherence, in which case we're looking at the phase as well. And then we can look at the spectral diversity between them, which gives us even better accuracy. And that's basically what we are doing for TOPS. We're using enhanced spectral diversity to be able to register them to the 1,000th of a pixel accuracy that we need. Then we resample the one image to the other, and then I wrote that here, that results need to be checked and the parameters may need to be adjusted, right? And I wrote that for good reason. And the reason is experience, and experience also with students, and it's it works very well, image registration in SAR images. However, there are situations where the automatic registration may fail, right? And then depending on the software that you have, the software may tell you that it failed. It may give you a warning that it thinks it may have failed. But you need to look at that. You need to look at that warning. There would be step number one. You need to look at the warning. And step number B is there are situations where the software itself is unaware that now it did not co-register them correctly. That can happen. That's even more seldom now. We have some ways to check to see, if all the parameters look right. But it still can happen. and it is very much advised to look at it and take a look by yourself if the resampling worked. That's especially true. Later, we will talk on persistent scatter interferometry, where we then use not one image or two images, but many, many images, right? So you're going to automatically co-register 20, 30, maybe 100 images. Now, what happens then if one or two or a couple of images are co-registered not correctly? Will you ever find that anymore if you do not check that? These are then errors that goes throughout all of your processing and may cause you errors and problems that is later hard to find. Okay, if you have then, if they don't match, and later your interferometry, your results look not like you wish them to look, right? Look wrong, and it's because of image registration failure. It's going to be later very difficult to find that. Okay, and I talk here from experience, because we went through that more than once, where we at the end find out that it was already the image registration that did not really work. So that can be the case. Okay. So after we do that, we register one image to the next image, right? It's typically just most of the times you can assume it's only an affine transformation, but you can also assume a second polynomial transformation. The way we do that is, so we determine the co-registration parameters. We look at a large number of image chips, that small parts of the image that we spread over the image, more than 100 image chips. Really, we use 1,000 or 2,000, 3,000 image chips, something like that nowadays, because now the computers can handle it. We also we have already some a priori information from the orbit. So we know the orbit. We can already have a rough shift based on the orbit and the DEM. And then we can set the image chips there and calculate them. And we use then some oversampling, interpolate the correlation peaks, and we get then the position of hundreds of these image chips. And then we use regression to parameterize the co-registration to go to get the co-registration parameters there. So we just go through that. Basically, we assume the parameters, then we kick out the outliers, assume it again, kick out the outliers until we are satisfied with our